Hello, everybody. Happy early morning. It's here Saturday at 1. I want to make sure that we have, the correct information to get started on our graphs. So first off, we're going to go ahead and do a sample of how to get started on part 1. So I made kind of a copy of it, but I kind of changed some of the stuff here so that y'all have like a way to get started on how to recreate your models. So I kind of just changed some dates around. So instead, I'm having my graph of sea levels be from 1940 to 1960. Again, we're trying to recreate the polynomial fit. Basically, that means we're trying to create a smooth data graph. This right here over the 10 years being averaged, that really doesn't tell us much other than the fact that we're using a polynomial fit. Okay, so unfortunately your laptop is broken and you can't project your graph to the city council, right? So again, this is our goal. We got to create the smoothed graph, but we do have these key features. So I do have that in 1940 at the start. The mean sea level was 5.3 millimeters above the sensor line. The average rates of increase in the sea level between 1940 and 1960 was 1.2 millimeters per year. Because I see millimeters per year, I know that's a rate. And rates of change, if we go back to my big ideas packet, it's mentioned in big idea number 1. Like for example, the area under a rate graph. It's also mentioned when we talk about velocity. So velocity is a rate, and usually we find these by calculating the slope between the 2 points on a position graph. Now, you could still, with water waves, you could still create a sort of position graph. Instead of like side to side motion or forward and backward motion, the sea levels are moving up and down. So we can still find on average how they're moving up and down. And again, we're given that on average between 1940 and 1960, it's 1.2 millimeters per year. Okay, that's an essential piece of information. So the mean sea level for my example that I have here changed directions 4 times between those 20 years. As a result, the graph had 4 relative extrema between its endpoints. So extrema, again, it's in the big ideas packet. It's basically those low and high points. So I had 7.06 millimeters in 1945, negative 7.5 millimeters in 1950, 10.54 millimeters in 1955, and negative 3.22 millimeters in 1958. So based on these facts, recreate your graph of mean sea levels between 1940 and 1960 as a sketch. Time should be the x-axis and the mean sea level should be the y-axis. So again, this is super important because now at least I know to get started how to label my graph. And then don't forget your units. All right, y'all, let's get started. Let's do this with all the information we've got. I'm going to be using my handy dandy annotation tools. What color do we have? I want black. Okay, and there we go. Here's my time, the x-axis. Let's label our stuff. So we got our mean sea level up here, and I'm gonna type this out. I'm just gonna put sea level, and it's in millimeters. You could think of this like your position graph. Because remember, this is like a position graph. It's like up and down motion instead of forward and side to side motion. And that's my y-axis. And down here, my x-axis will just be regular old time. And I'm going to go ahead and just relabel this as y-axis. And this is my x-axis. And I know x represents t here, but yeah. Okay, next thing you want to do is you want to put your sensor. So the sensor, I think, makes the most sense to kind of put it right here in the origin on the y. Basically, it's measuring ups and downs of the waves, and the sensor would be right here because it measures positives and negatives. So we're going to say the sensor is at the origin. Here we go. All right, so next thing is I'm going to have to try to tick off how to count on my stuff. I know on the x-axis, we start at 1940 right here on x, and then we go over to 1960. So let's take care of that. So let's say the time starts right here at 1940. And I'm going to go up to 1960. Let me count by fives. I'm going to try to spread this out. 1945, 1950, 1955, and 1960. Say this is 1960. There we go. All right, next, let's go ahead and try to tick off our y-axis. So how I do that is I take a look at what are my, like, you know, the highest and lowest points. So I have 10, and then I have negative 3.22. Okay, so I'm going to maybe tick it off until I reach at least 10 up in the positive and down in the negative. So for this one, I probably want to count to twos. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. So again, just making sure that, so it's okay if I count here by twos, just make sure that it's equally spaced. And over here, I counted by fives for the horizontal axis, making sure that's equally spaced. So this looks about equally spaced. You can use a ruler if you want to make it more perfect, so forth. All right, let's put down what we got. So let's go, let's do this. I just want to scroll up to see when at 1940, the mean sea level was 5.33 millimeters above the sensor line. All right, 1940. I'm going to use red. So at 1940, right here at the start of time, it was, and I already forgot, 5.33. And maybe I shouldn't scroll as down. Yeah, just keep that. 5.33, and I know this was 2, 4, 6, and 5.33. Let's say it's around here. It's just an estimate. Okay. The average rate of increase. Now, the average rate between these 2 points is 1.22 millimeters per year. I'm going to kind of come back to that because that's, although in order to find the average rate between these 2 points, I have to first get here. So I want to first figure out what's happening in between here. So I'm going to come back to that second bullet about the average rate because that's basically involving my last point only. So let's move on to what other information we can get. The mean sea level change directions 4 times. So change in directions 4 times. Again, if you look at your big ideas packet, change in direction happens when the slope goes from, in a position graph, when the slope goes from a positive, like for example, if I have a position graph and it looks something like this, and this is a position graph. That means this could be P position, like in distance. And then we got time. If in a position graph I'm moving forward, that's a positive slope. And then if I'm moving backwards, that's a negative slope. In other words, positive velocity, negative velocity. Whenever that change happens, you have either a maximum point or you have a minimum point, actually, if you think of it backwards. So basically, change in direction happens at the extrema in a position graph. And this sea level is basically like our position graphs, because instead of moving side to side, it's moving up and down. So we could think of it like that. So that's just the background. So I need 4 extrema, and that's also outlined here. There's 4 relative extrema between the endpoints, so excluding the endpoints. And they give us where that relative extrema are found at, right here. All right, go ahead and erase that. That was just for further explanation and clarification. Okay, awesome. Let's get back to it. So cool. So great. I have that piece of information, and we're given the extremas. Let's locate them. 1945 at 7.06. So this is 1945. It's 246, and probably around here. There's like a slight increase up here. And it's going to be negative 7.55 in 1950. So down here about. And then 10.54 in 1955. 10, 2, 4, 6, 8, 10. Again, if you have a ruler, so I'm just trying to make sure that's about 10.55. It's neater. Then 1958, so 1958 somewhere above 1960, it's negative 3.22, so somewhere down here. And then we still need the point at 1960, and I'm going to be using the average rate of change information to figure out that last point. But for now, let's go ahead and fill in what we got so far. Maybe I'll use blue. So I know that according to using polynomial fit and statistics, my graph needs to look smooth. So I have to try to connect this with smooth lines. There we go. By the way, this is lower. This point is lower than this point. So this is a slight maximum, slight extrema right here. And it's going to go here. I'm trying to make like a smooth kind of curve between the points. That's looking okay. And well, here we go. So far between the endpoints, I mean, I'm still missing an endpoint right here. So my endpoint's still missing right here, but I have 1, 2, 3, 4. That's still because we're missing that last endpoint. But between the endpoints, right, between this point and the last point, I have 1, 2, 3, 4. 4 extrema, 4 changes in direction. And again, you could take a look at the big ideas packet for why that makes sense and why I'm changing why the sea levels are changing their directions from up to down. Again, take a look at the slopes. So that verifies so far what's in this video. Now then, we got to figure out that last point, and what we're going to be using is average rates. Again, if you look at your big ideas packet, how to find average rate of change is the slope between 2 points. Now, I could go back to it and show you, but you guys can go ahead and go back. As you know, to find the average rate of change between 2 points is you find the slope between the 2 points. Let me just write down the slope formula right here again. So it's y2 minus y1 all over x2 minus x1. And I know that that slope, according to what they gave me right here, the rate is 1.2 millimeters per year. So it's 1.22. So I'm just gonna write that down. All right. And I also have additional information. So for example, at 1940, this point right here, 1940 comma, no, what was it, 5.33? That was the first point. Then my last point, I don't know it, but I do know that it's going to be 1960 comma something. And I'm going to put question mark there. Okay, cool. So I have information. So let's go ahead and plug it in. So this is x1, y1, x2, and y2. Okay, let's plug it in. So y2 is question mark. Y1 is 5.33. 3 all over. And then x2 is 1960 minus 1940. And we still got that this is equal to 1.22. All right, so cool. Of course, let's simplify the bottom up. So I got question mark minus 5.33 over 20 is equal to 1.22. Awesome, awesome. We're getting there. We got to figure out what question mark is. We're going to get some more information. So right here, to go ahead and get the question mark by itself, what I'm going to do is I'm going to multiply both sides by 20. The opposite of division is multiplication. Multiply by 20. That cancels out. Go back to blue. So we have question mark minus 5.33 equals, and I'm going to use the calculator, 1.22 times 20. It's going to give me 24.4. Cool. So that's 24.4. Now to solve for question mark, we're going to add 5.33 both sides. So then we get question mark to be, it's going to be a big number, 29.73 maybe? No, I don't think it's that. Yeah, 29.73 if you add that up, right? I'm going to double check. Yep, I guess I shouldn't doubt myself on that. Okay, so it's going to be 29.73. Wow, so that sea level rose quite a bit. So the question mark is 29.73. And therefore, that point goes really high. It's going to go off my graph once again, all the way up here. I'm estimating 20s all the way up there. And we go ahead and we finish our curve there, like so. There we are. So there's my model here for this new data. You want to verify it changes directions 4 times between the 20 years, so excluding the endpoints, and that it fits all of that. So I think we got it, and you could, double check that the average rate, which is, let me change my color. The average rate from here to here, the average rate of increase is 1.22 millimeters per year. By the way, if any of you, and by the way, the average rate, what I mean by that is like you're finding like the rise over run. So over time, we get that between here and here, rise over run. You get 1.22 millimeters per year if you count that. Like each time you rise over per year though. So that's why it looks huge over time. That's why it grew so high. But yeah, that's just as a double check there so you can verify your data. If you're able to use Desmos on this, let me know. It's gonna be awesome if you're able to create some smooth data with Desmos. If not, you can use a piece of paper or you could use any drawing tools like I have used here, as long as it fits the data. All right, everybody, good luck. Thank you. And let me